Ladies and gentlemen, a warm welcome to the fourth day of 5-day national workshop on applied mathematics and computing organized by the Madhav Institute of Technology and Science, Gwalior. Sir, am I audible?
Yes, you are audible, beta.
Okay, sir. We are honored to have esteemed and renowned speakers, dedicated faculty members, and participants joining us for this enriching event. Dear participants, we are honored to have with us today an esteemed speaker who will enlightening us on the topic real-time application of graph theory. Now, I would like to introduce our distinguished speaker, Dr. M. Sindhu. Dr. M. Sindhu is a renowned assistant professor of mathematics in Excel Engineering College Autonomous in Namakkal, Tamil Nadu. With a profound experience of around 6 years, she has made significant contribution to the field of real-time application of graph theory. Her expertise and research mainly focuses on graph theory. Dr. M. Sindhu's academic journey encompasses an impressive range of accomplishments. She has been a class advisor for 5 years and guided students for paper presentation on topics such as cryptography, image processing, and golden ratio. Her dedication to the field of mathematics extends beyond academia. She has done research on graph labeling, which is an important part of graph theory, for 3 years. She has published numerous research papers for UGC Carelist Group 1, Scopus, peer-reviewed journals, published a book chapter, and presented research papers in national and international conferences. Now, let us eagerly listen to Dr. M. Sindhu as she takes the stage to enlighten us with her expertise and insights.
Ma'am, are you there? Yeah.
Can you hear me, sir?
Yes, ma'am. We can hear you.
Okay, thank you, sir, for inviting me for this valuable workshop. Now I will go for the presentation.
Yes, ma'am.
The screen is visible, sir?
Yes, ma'am. It is clearly visible, ma'am.
Okay, sir, thank you. Good evening, everyone. This is Dr. M. Sindhu, and I thank the organizers for inviting me for this workshop. And thank you for giving me about the things what I did in the last 6 years. It was very grateful. And now we'll go for the presentation. Today's my topic was given as real-time applications of graph theory. So first we go for the history of graph theory, how it came, how the graph theory came into the existence. Startingly, it was began at the 1735. Euler, by the seven-bridge Königsberg problem, he introduced this graph. So this is the bridge what we have seen already. Many of you know that how this Königsberg problem came into existence. So this is the thing. Königsberg Bridge. They have Euler have worked on it, and he have given the graph. That is a Euler graph. So here the problem is
Sorry to
what the
interrupt
walk
you, ma'am.
all bridge. Yes, sir.
Ma'am, your slide is actually not moving.
Not moving, sir.
You better you click
Now
on
you
the
can
second
now you,
slide. Yes,
now you
yes,
can see,
yes,
sir.
ma'am. Now it is
Yeah.
visible.
Oh,
Yes, yes, yes.
okay. Oh, okay, sir. So Euler only started this the problem. That is, he has introduced a problem that is walk on 7 bridges without crossing a bridge twice. So from this only we have came into the theory of graph. So from the Königsberg's problem only we have known about this graph, Euler graph. So this was the origin of the graph theory. So next is they have seen the Königsberg problem. Then the polyhedra cycles of the polyhedra was read by Thomas and Hamilton. We all know about this Hamiltonian graph and Hamiltonian path and all. So these people have worked on this and they have given this Hamiltonian graph and all. So first we'll see about what is the definition of a graph. So graph means it has nodes and edges. Nodes means we have seen that this we are saying as vertices. So here they can denote as nodes also. So nodes and edges. So we simply write as G is equal to V comma E. So V means nodes or vertices or points. E means edges, that is links or arcs, that is the line which is joining the vertices, we are saying as edges between the pair of nodes. So graph size, that is parameters means we seeing that n. N means the cardinality, how many vertices you are having that we are representing as n, and the cardinality of E, number of edges in the graph, the cardinality of the edges will be m. So these are some basic concepts of graph. So an example of a graph. So how we have seen this already. We have many of you have done this graph. We know we have studied this graph. So we know all know what is a graph. So we'll be having some vertices and we'll be having some edges. So here we are taking a graph. That graph has how many? That is n is equal to six. 6 vertices we are having, and m is equal to 7. That is the number of edges in this graph is 7. So we are denoted this V as 1, 2, 3 up to 6, and edges as the edges connecting the vertices. That is 1 comma 2, 1 comma 5, like that it goes on, and up to 4 comma 6. So the neighborhood of, suppose you are saying if you want to know about what is the neighborhood of 4, then we can say as 6, 5, and 3. They are the neighborhood of 4. So next we go for the main part of this presentation, that is applications of graph theory. So it is having a vast applications in many of the fields. So if I take graph theory as a middleman, we can see we have using in Google Maps, we are using in computer science field, we are using, and in networking, you are using electrical engineering, you are using maths and operations research, you are using physics, chemistry, you are using, and social science and linguistics, you are using. This is a somewhat pictorial representation of this graph theory where we are using. So we'll see detailedly about this. Graph theory applications in computer science, where we are using this graph theory in computer science. So we are using it mainly on networks. So for connecting data, we are reaching peoples, we are using this networks. So that is main of communications, data organization, computation devices. In that we are using graphs, and for computation flow, we are using this many rules for binding some rules. We are using this graphs. And database, in databases also we are using this graph theory. So mainly many people have worked on this digitized algorithms. So many of come across this digitized algorithms. This is to find the shortest path between two vertices. So to find the shortest path, but we are this algorithm is used in computer science for finding some the minimum route, the minimum route or shortest path, you can say. For that, we are using this digitized algorithm. So it has a lot of applications in this. Many papers have been written in this digitized algorithms. It is a new thing, but it is very focusable. So here we are seeing that minimum spanning tree problem. We are having some minimum spanning tree. It's same like this only. That is, we are finding the minimum weight. We are finding the lowest total weight of the connections between vertices, such that it is a path in the graph for every vertex to another vertex. So we are finding the minimum weight. So or otherwise we can say by the shortest path. So that is the digitized algorithm main aim. And we are having other algorithms also. That is Kruskal's algorithm and Prim's algorithms. This is also a kind of algorithms for finding this minimum route or minimum path. So here, this algorithms they are used in the electricity network in between the hubs in the real world. So there are a lot of possible connections. So if you are connecting any people, we are having so many connections. So many. If you are taking internet, also we are having so many connections. So many lands we are using. So for that, to reach someone can use a shortest method, shortest path. So for that, this algorithm is very useful to reduce the cost also. So this is a problem. So I have given some how they are working on this. So this is a algorithm of graph with no negative weights. So you don't have any negative weights, and this is a path weight. We are finding the path weight, the vertex that is close to the source. So we keep the track of minimum path weight among all the paths from the source we have found so far. So you see, this is the graph. We are having the length. So length of A, B, C, and E will be 6, and distance from A to E will be 5. So A is in the graph here. A is here and E is here. So for reaching this, the distance is 6. We are saying. So we are moving from one place to another by crossing all these vertices. So by using this algorithm, we can find the minimum weight so that we can each reach this easily. So this is a method we are using to find the shortest path. So digits mainly used in the finding the shortest path. So to lower the time, to lower your cost and all. So this is a spanning tree. Spanning tree, already we know what is a spanning tree. It is a subgraph of the tree. It connects all the vertices. So you'll be having all the vertices, but it is a subgraph of the main tree. So that is the spanning tree. So see here, you are having an example. This graph, we are having a spanning tree 1, spanning tree 2, and spanning tree 3. So this is the possibilities for the spanning trees. So we are here, all the spanning tree all has all the vertices, but we have to find the minimum spanning tree. That is, we have to find the minimum weight of the spanning tree. That is, the weight of the graph should be low. So comparatively with the other graphs, so which graphs gives you the lowest weight? That is your minimum spanning tree. So again, the Kruskal's algorithm. So it is a method for finding shortest spanning tree in the given graph, both by hand and by computer. So we can use by you can work out by the paper, or we can work out in the computer also. We are having all the softwares for this, and we can find the shortest path. Next is Prim's algorithm. So another algorithm does not need to change list all the edges in order of decreasing weight or to check up at each step if a newly selected edge forms a circuit. So that is, here also we are using that circuit based things. That is, we are finding the shortest weight, shortest path, so by the weight of the graph. So in computer programming also we are using this graph theory. So here a program can be represented by a digraph, which is very convenient. Every vertex represents a program block, and each edge that is vi, vj represents a possible transfer of control from the last instruction in the program block v to the first instruction to the program block vj. This type of digraph is known as program diagram. So we are using this graph in the programming also. They are saying this is a programming diagram. So program diagram. So here there is a program diagram, is a simplified version of flow chart in which the boxes have been shrunk into vertices and the arrow have been transformed into edges. So here having the blocks, that blocks we are representing as vertices, and the connection between the blocks we are representing as edges. That is the arrows here. So this is called as programming. So it is an mere example of this program diagraph will be your flow chart. So here, your flowchart, we are having some decision box, start box, stop box, and all. So they are be connected by the arrowheads. So the arrowheads will be acting as edges, and the boxes will be acting as your vertices. Next one is graph theory applications in computer network. So before that, we seen that computer programming. Now we are going to see about how the application is used in the graph computer network. The principle of graph theory governs the relations between the interconnected computers in network. So as usual, you're connected by the network. So this networks, how they are using this graph theory. So here they are using as topology. That networking is called as here topology. A topology in a computer network is used to explain how a network is physically connected as well as logical flow for information in the network. So in terms, the topology primarily describes how devices are linked and interact with each other using the communication links. So here that topology, that is a connection, combination of all the networks, that is the computer networks. So here they are having some, we are connecting the people by the networks. So this is called as topology. A network of communications are represented by using graph theory. Graphs are used to describe the computation flow. So we are using this graph theory for the computation flow. Graphs are used for the computation for how it is flows from where to where it moves. So we can use graphs for that. Network security also makes use of this graph theory. So we are using this network security for when the graph theory is used in the network security also. Next one is GSM. Already we know this word GSM, grouped science special mobile. Grouped special mobile means that is we are having some GSM mobiles. So the mobile networks we are having. So the vertex coloring algorithm is used to assign the more at most four different frequencies. So we are having many frequencies. So here that is GSM is used. The vertex coloring algorithm is used to find a suitable four color coloring of for the map. So we are using this again. Graph theory is used in terms of coloring algorithm, vertex coloring algorithm in the GSM mobile network also. Next one is application of graph theory in electrical engineering. By using this graph theory in electrical engineering, it is used in designing of circuit connections in electrical engineering. These connections are referred as topologies. Already, this topology's name we have seen in the computer networking. So here in electrical engineering also seeing this topology. Topology, in other words, the arrangement of communication networks elements called topologies. The topologies of a network is studied through its graph. So topology means it's a graph. So we'll be having the vertices and edges. So we are giving a different name in the engineering field. It is called as topology. The star, bridge, mesh, tree, ring, circular, hybrid. So these are the some of the topologies. We'll be having some different types of connections. So they are saying as a star, okay, the connection of a star, bridge, or it may be a mesh, or it may be a tree. So this is a different given, and different configuration nodes and links to be and the best network topology of each business is determined by the size, scale, goals, and budget. So according to the budget of this business, what we are going to do, so according to that the topology can be defined. So because of the few different electrical elements, the variations in networks is primarily caused by the variation in the topology. So topology brings a main role in the electric networking. So here they are using many. We have to study on this, and we have to use properly for the networking purpose. In drawing a graph of electrical network, regardless of the nature and size of the electrical elements, junctions are denoted by the vertices. So as usual, I've told that junctions that we are saying as vertices, and the branches what we are giving as edges. So in the programming, that is in computer programming, we have known these vertices are called as blocks and arrows, and here they are denoting as junctions and branches. So the different names only they are given in the different field, but the usage of this graph is mainly they are using the it's a main role in all the engineering field. Next, how we are using this mathematics in graph theory. Graph was used in geometry, certain aspects of topology such as knot theory in the mathematics. In operations research also we are using this mathematics. It's a significant area of study in the mathematics. Minimum cost path, already we seen this minimum cost path or cheapest route. We'll be saying that, and the scheduling problems are two examples of useful application in operations research. So we have seen this operation research. Finding the minimum cost path and scheduling problem, they are the main role we are using this graph theory. How we are using this graph theory in operations research, detail we can see. We are using in modeling, transportation, network activity, game theory. We are using this large number of computational problems are used in using network activity, and planning and scheduling large complex projects are one of the most popular and successful applications of networks in the operation research. So planning and scheduling, by using this planning and in scheduling, the graph theory is used, and we have seen this part already. We have studied, I think so. This part project evaluation review technique and CPM method, critical path method. So we have come across these two things. If you have studied this operation research, so this is used. The graph theory is used here to find the uh, shortest path. To find the best way to perform specific tasks in the competitive situations, game theory is applied in the problems in engineering, economics, and war science, etc. In case of vertices represents the positions and the edges represents the movements. So here the vertices they are naming as positions and the edges are movements. So different names for these vertices and edges. The wherever the field goes, the names it gets differed, but the application is very useful. Next was graph coloring techniques. So a graph coloring is the most important concepts in graph theory. Proper coloring of a graph is the coloring of vertices and edges, minimal number of colors. So already we have seen this. We are using this four color problem, or we having this vertex coloring algorithm and all. We are using this graph coloring techniques. So that two adjacent edges will not get the same color. So not color with the same color. The adjacent edges should not have the same color. That is the technique. This technique is made in selecting many scheduling problems such as job scheduling, aircraft scheduling, um, by process tasks and timetabling also we used this. And on an example given, that is timetable scheduling, where we are using this timetable scheduling, timetabling is the most complex error prone problem. So because while we are all I know many of them are assistant professors, or we are working on colleges. So we'll be using this timetable to find out the timetable. We should not put in should not clash the hours. So it's a very big task for us to do this. So here we are using this graph coloring techniques to find a easy way to do this timetable scheduling. Therefore, it's a great requirement of an application which is distribute the courses evenly and without collisions. That is, without clashing the hours, and properly every day, every hour should come. So that is a main task for us. So for timetable scheduling, we are using this graph theory, and we are doing by the graph coloring technique, we can use that. Particular form of timetable required a specific to the environment and the institutions in which it is needed. For example, a school timetabling problem and a university timetabling problem at the first instance seem to be the same problem, but with a different. There are many differences because every semester we'll be using this timetable. So it will differ upon, and it will be getting a difference. Every semester it will be in a different manner. So you may be having the same last semester timetable will not be the same as the next semester timetable. So it gets differences. So we'll be having many differences in this. In such differences in that school class sizes at most similar and all rooms are sufficiently large enough. So here the number of students in the class, number of courses in new courses if you have been introduced, so we have to put the timetable for that also. So this timetable schedule will be helpful for that. On the other hand, in university, size class can range from 5 to 200 students. In fact, problem may be changed even within one institutions also. Graph coloring techniques plays an important role in all such. So this graph coloring techniques we are using timetable schedule. So this is a problem, simple problem in timetable scheduling. We have 5 courses: physics, chemistry, biology, maths, and biology. So if you see here, you are having a diagram. This is representing this timetable. Graph showing timetable conflict between them, where the vertices represents the subjects and edges. The between them represent conflict. that is no two adjacent edges can together be scheduled. So if you have scheduling physics for 1 hour, next hour only we can schedule for chemistry, then next hour only for mathematics. So all the courses will be on the same time, so that we will be giving a different colors for the edges. So adjacent edges, here the physics is adjacent to chemistry, so we are giving different color. So here it is red and here it is green. And chemistry and mathematics we are having a it is adjacent but we are having a different color. So to represent this graph coloring, by using this graph coloring we are giving this timetabling scheduling, very easy to do. And for scheduling an exam, also it is very difficult for us to do schedule exams for courses. Two courses clash if some student taking on them both. Suppose we are just taking for course, two courses get clashed. So 9 is obviously suffix for the. This is an example of this graph coloring. So here they are using this. They are using giving different. They're giving a same color for the subject. If you are having physics, chemistry, and maths means so physics one color, chemistry one color, and maths one color, and we can use the exams also. So the course they are giving vertex and clashing the edges. They are giving a better line. So graph color they are use Sudoku also. Graph coloring is a powerful tool for solving problems. Can be applied for solve real world problem many fields, and even solve puzzles like Sudoku. The application of graph theory is solving Sudoku puzzles in real life examples. So we have come across this puzzle. So it be having numbers, and you have to fill the numbers so that is with the summations with numbers. So that is it's a main application of the graph theory which is used in the Sudoku puzzle. Individual cells on the Sudoku get colored using the graph coloring. So here we are using this graph coloring also. Each cell must be assigned a color, and no two cells of the same color can be adjacent. So in Sudoku we are using numbers from 0 to 9. So same numbers cannot be there at adjacent. So say the same technique we are using in the graph coloring also. So each cell will be assigned color, and no two cells of the cell can be adjacent. So two cell have the same, so it have a different color. Graph coloring is used in the Sudoku also. To do this, assign a color to each vertex and check to ensure that no two adjacent cells have the same color. So here you'll be having three-dimensional puzzles, graph coloring and image problems and circuit designs also. For example, efficient circuits, cross and few transistors can be designed using graph coloring. In addition, graph coloring can solve the traveling salesman problem. So this also we have seen traveling salesman problem. Many have known if you have studied OR. Traveling salesman problem. It is an important problem in computer science also. It is a salesman must visit a set of cities while minimizing the total cost of the travel. So you have to visit the cities by with a low cost. Graph coloring can be used to determine the shortest route between the cities by assigning colors to the edges of the graph. So the traveling salesman problem also we are using this graph color. So graph color, we are not giving the same color to the adjacent cities. That's the difference. So this is an example of Sudoku. So this is a Sudoku puzzle you already known. So 1 to 16 numbers we have assigned, and they are given the different colors. See that you are having no colors the same adjacent to it. So all the vertices are different colors. So by this you can color, and this is the 1 to 16 you are having not in a suitable puzzle is in way. After we graph coloring, and we are now given in the and coloring maps. This coloring maps is also we are using that same cities have the cities don't have the same color. So different cities will have different colors, and here the regions are vertices and neighboring are edges. So here, if you are having a map like this, if you are having any state or city you are having, so the nearest cities won't get this color. Adjacent we should have different colors, so that we are using the graph coloring. Map scheduling. Aircraft scheduling is roughly described as we are having like timetable scheduling. This aircraft scheduling is also a wide role. We have to schedule the aircraft for landing purpose. So input a set of aircraft and a set of flights. Output the individual roster of each aircraft so that all flights are assigned. So timetable of flights is fixed. Departure arrival times when the starting the aircraft scheduling. The type of the aircraft is not decided. So according to passengers, they see the aircraft can be which flight can be used. So for example, we are having Boeing 767 can take twice as many passengers as DC-9 and also can fly longer distance. Boeing can fly longer distance, whereas DC-9 cannot fly that much. So according to they will be scheduling, they will be allocating the passengers. So for aircraft scheduling also we are using this graph coloring. So applications of graph theory, physics and chemistry. So how we are using in physics and chemistry this graph theory we'll see. In chemistry and physics we studied molecules because graphs represent the substance, molecular and chemical structures, etc. A graph can construct a molecular structure, lattice of any molecule. It is also aids in showing the bonding relationship between atoms and molecules, as well as comparing the structure of one molecule to another. So here, this graph is used in structuring the molecules. So the relationship between the bonds and molecules we are representing by the where we'll be connecting by the lines. That is the edges here. With the help of the graphs, the 3D structure of the complicated simulated atomic structures can be quantitatively studied by gathering data on the graph theoretic properties related to the atomic topology. So here we are having 3D structures also. We have seen the structures of chemistry. We are having, suppose we are having any chemical compound, it will be can represent by a 3D structure. So we'll be having all the components and molecules what we are using in that component. So we can represent by this graphic theoretical structures. Graphs in statistical physics can represent the local connections between the interacting parts of a system as well the dynamics of a physical process on the such systems. So graphs plays an important role in the statistical physics also. This is the structure. The chemical bond we'll be having and we'll be linking these all these by the edges. So this molecules will be having as we'll be saying as vertices and connected by the line at the edge. So it is the molecular structure of a chemical component. So application of graph theory in biology. So where we are using this application in biology, we'll see. In biology, a graph is used to map out networks of genes and proteins and analyze the interaction between two different components. So we are using this graph theory in analyzing the interaction between the components, that is genes and proteins we are using. DNA structure is DNA structure is also an example of a graph. It's an organism, biological networks, and neural networks. So it is made up of the DNA structure is made up of the organisms, biological networks, and neural networks. So they are also the representation of the graphs. Nodes in biological networks represent the biomolecules such as genes, proteins, and metabolites. And edges connecting these nodes indicate functional, physical, and chemical interactions between the corresponding biomolecules. So we are connecting these nodes. The nodes are the biological networks, molecules of genes. So genes and proteins we are connecting by the edges, which gives the functional and chemical interaction between molecules. Graph is also used in metabolic networks and transcriptional regulation networks. Graph theory is used in the PP, that is protein interaction networks, and data-sizing drug target relationships. So we are using this protein interactions also. We are using this graph theory. So this is a food chain. So how this is grasshopper eats eaten by the then the frog is by the snake and snake by the hand. It forms a fungi and is hybridizes a fungi again it produces gases. So it is a networking. Again here we are seeing the networking. So these are the vertices and we are connected by the edges. So it is also an example of a graph theory. So application of graph theory in social science. So why we are using the social science? How we are using this graph theory. Socially makes extensive use of graph theory also. For example, using graphs of apprenticeships, whether or not we are there. So in social networking also we are using this graph theory. Using social network analysis software to investigate rumor spreading or access actors' reputations. So for spreading new rumors or also we are using this analyzing software to find out which the spreading of the rumor, and using the influence of graph model to influence the behavior of others by certain individuals. So you have to can use this influence graph models to find the influence of the behavior, and using the collaboration graphs to examine whether two people collaborate in a special way, such as working in a team together. So collaboration graphs also they are using. So this is an network modeled as a graph. So we are having a social network. So we are having a WhatsApp network. We are having a Facebook. Also, we are having some networks. We are having community and all. All this based on the graph. We know all. We are all the. We will be acting as a vertices, and we are connected by the other person by the edges. So this is a modeled graph. So the social network is modeled as a graph. So here you're having the friends and your relatives, they are connected by the ages. And this is watch Netflix, he can go with a friend, he listen to the song. So this person, concerned person have so many networks. So this is also a networking. According to this person, he likes to cook, he like to see some movies, and he likes to go out. So all these all networking only. To reach some place, we are using this networking. So next is the internet. For what is the internet? Already we are all familiar with this internet. So internet is a virtual graph. It's a virtual graph. Every vertex is an individual web page, and every edge means that there is a hyperlink between the two pages. A node that links only go one way. So this graph is, and the graph is very very large. So this graph we can see that it connects everything in this world. That is, we can connect all the social medias and all the networking platforms, and we can connect to the persons those who are in abroad by all these network internet. So this is a wide graph, that is a virtual graph. We are connecting the peoples. Some websites like Wikipedia and Facebook have a lot of incoming links, and while many smaller websites may have very few incoming links, this is underlining concept which is Google uses to sort some results. So this is a networking. So how we are using all the in platforms we are using, they are all connected with the network. So this is the application of graph theory used in healthcare, where we are using in healthcare also we are using this graphic technology. Decision medicine. So graph algorithms can transfer interconnected drug, gene disease, and patient networks to help understand disease drug gene patient interactions. So we can predict the medicines. What medicines we have to find. They are all interconnected. With the graphic algorithms, we can use this. And drug retargeting. By analyzing a graph of disease and drug nodes, new target proteins can be identified for existing. So for drug retargeting, we're using this graphic. Economics and disease risk prediction. A graph of disease and genes with connections between moderate diseases, related genes, and known disease gene associations could help uncover new associations. And fraud detection, we are using this graph. Graph methods can help to log the entire health network to detect collusions, and all these fake referrals also we can find by the database for electronic health record. So for if we are maintaining, we are having a record means we will be having some many medical records. So that medical records we are having will be stored in the graph database, so we can easily fetch that when we want. So this is an example. This is an database we are using for graph database. We can get the applications. We can help. Can get the data about the patient. So next one is application of graph theory in linguistics. Linguistics is a science of language and it includes in cinematics, syntax, phonetics, phonology, morphology, historical linguistic, etc. The linguistic graphs are used to parsing blanks. The words denote words and word strings, while edges denote the entire relationship between them. So the words will be denoted as words, and the relations they are between the words. We are using these edges. So that is used in this linguistics. A set of words vocabulary and a set of rules are forming strings and define a language. This that is a language is a collection of all the legally generated strings. The computational linguistics one problem is to identify whether a given string belongs to a language with a given vocabulary and grammar. In linguistics, graphs are mostly used for parsing tree of a language and grammar of language. There is a rooted, ordered tree that represents a syntactic structure for the parse tree. So we use this graph theory in MITS also. So this is a network graph formed by the Wikipedia. So here we are all having all the languages which are the contributing different Wikipedia languages. Different Wikipedia languages they have gathered and they have formed as a graph. It is done by Wikipedia. So application of graph theory in GSM mobile phone networks and map coloring. All mobile phones connected to GSM network by scanning for the nearby cells. For example, any GSM mobile network, the vertex coloring, already we seen this already vertex coloring algorithm to allocate at most four distinct frequencies. To allocate for we all are having many networks, many private networks we are having, government networks we are having. All these things we are connecting by the according to the frequencies we are giving the preference and the vertex coloring algorithm is used here. Applications of graph theory in Google Maps. How we are using in Google Map. The main thing we are using in Google Map to find some places. If you are new to any city, we want to reach some places. We are using this Google Map. But to find places in
Ma'am, are you available there? Ma'am, can you hear me? Dr. M. Sindhu, ma'am, can you hear me? I think ma'am is having some network issue, so please wait. She'll be joined soon. Now you can fill the feedback form and give the quiz. Please check the chat box for the given link.
Hello, sir. Can you hear me, sir?
Yes, ma'am, you are audible.
My screen is visible, ma'am.
Yes, yes, ma'am, it's visible.
Okay, thank you. Sorry for the problem inconvenience because of the network issue. I got cut. So we'll see about this application of graph theory in Google Maps. Where we are using this graph theory in Google Maps, we'll see. Graph theory is used to find the shortest route in the network and on the road. For example, graph theory is used to find the shortest path the house by the GPS. So in Google Maps, different locations are represented as vertices and nodes, and roads are represented as edges. With graph theory used to find the shortest path between the two nodes. Graph theory has an applications many other fields such as economics, sociology, psychology, and its usefulness and versatility make it a valuable tool for solving real world problems. How we are using this GPS to find the route based on the user preferences, that is the shortest route. Suppose we are using this Google map, you'll be seeing this where to, you'll be having many routes to reach the place, but we'll be choosing only the shortest distance to reach the place. So for that we are using this graph theory to find the cheapest fare between the two locations. In case the locations are represented by the vertices and the connections are represented by the edges that contain information such as the distance and fare. Based on the user setting, the software evaluates the critical path. That is the optimal route we will be finding out. This is helpful for us to know the timing to reach the place or the cost for the fare. That is the fare we are using for reaching the place that will be reduced. Next is map networks. Map networks such as Maze, Google Maps, Apple Maps, and the Uber are installed on all the smartphones. Navigation problems can are model like graph problems. Think of the examples like traveling merchant problems, shortcut problems, Hamilton routes, etc. So graph theory is used in traffic lights also. Graph theory is used in operations of traffic lights, specifically the turning the green and red, the timing between them. So in graph theory is also used in the graphic traffic lights. So for turning green and red lights. Here we use the vertex coloring technique. Again, the vertex coloring technique is used to resolve time and space conflicts by identifying the chromatic number of cycles required. Application of graph theory in solving crimes also. This application is used. In the real world, it's the most important application of graph theory. Graph theory can maybe aware that all about linking and analyzing of linking. It can assist you in tracing one who spread the false rumor to a mastermind of a serious crime. Graph methods can be used in criminal investigation systems. In case it is a suppose that the investigations people are represented by the vertices of the graph and the edges represents the possible connections. So suppose one person is there and he is spreading a false rumor. So we can find the that is a number. The people will be represented as vertices, and the linking between them is represented as the edges. And we are using this graph theory in blockchain also. This is a booming technology now with the technology which is we are using in many of the fields. It's a new technology that is a blockchain technology. The vertices are blocks and each holding multiple transactions and each the edges connected to the following blocks. The largest branch from the first block is current standard for historical transaction. This is an example of this blockchain diagram. Since we all having the vertices and the edges connecting to them, so it's an representation of this blockchain. Here also we are using this graph theory, that is the vertices and edges we are using. Next is application of graph theory in the field of internet. So already we are all connected by this internet and it is a virtual graph. And here having the search engines like Google and Yahoo, Bing and all we are using. These are also the application of this graph theory only, where the web pages are linked to each other on the internet via the hyperlinks. So here we'll be having some web pages. This web pages are they are linked by the hyperlinks. So this is also a vertex and the edges concept only are using here. In graph, every vertex represents a separate web page and every edge represents a link. There is a hyperlink between the two pages. So this algorithm we are using is page rank algorithm or Google Blot algorithm we are using for doing this process to move to one page to another. This is a page rank algorithm. So here the this ranking algorithm, page rank algorithm is used for switching from one page to another web page. So it is a main algorithm we are using in our day-to-day life. But this is a main concept. This is an example. This is an application of this graph theory. Main example of this graph theory. So this is how we are linked. All the networking what we are doing, and we are all linked by the social medias and all this platforms which are using in day-to-day life. Another field where we are using this graph theory. Graph theory is used in design computer chips. Chips also computer forming this producing the computer chips also we are using this graph theory to connect millions of transistors and consisting in integrated circuits. Graph theory is also used in computer network security. Graph theory concepts is used in computer hardware to model the physical layers in limitations. The main applications area of graph theory is data mining in a graph uh, is great graph mining. The relation aspects of the data is represented by graph mining. We use graph coloring techniques of graph theory in scheduling, as such as job scheduling, aircraft scheduling, etc. Graph theory is also used extremely in the field of computer science, particularly in the problems dealing with optimization. So already we've seen all these things that is called networking, optimization, finding the shortest path, and all we have seen. A graph theory can be used in create algorithms for finding the shortest path between 2 points or finding the most efficient solution for a problem. Graph theory is also used in artificial intelligence, which is a new thing we are using in the day-to-day life. That is AI, artificial intelligence we are using, where it is used to create algorithms for problem solving. So these are some applications other than we have discussed here. Some of the we are using in our day-to-day life. All the things we are using, which is based on this graph theory only, mainly on internet and all the computer networking and computer chips we are using and data mining also using all the new platforms, new softwares where we are using all this comes under some application is used regarding this graph theory. These are some applications where I have discussed here. I think it is be very useful for you where you are using this graph theory in your real time. So we are all connected by this graph theory only. All the networking and communications, what we are doing, we are all connected by this graph theory only. So it plays an important role in our day-to-day life. And thank you for listening to this my presentation.
Thank you, ma'am. Your session was really very nice,
Thank you,
with
sir.
some interruption of internet.
Okay, sir.
So, is there any question from the audience? You can type in the chat box. Ma'am, can you please share the PPT? Ma'am, students are asking about PPT. And is there any question from the audience? I guess there is no question. So, ma'am, thank you so much. Ayushi,
Thank you, sir.
please carry on, better. Ayushi, switch on your mic.
Sorry, sir. Uh, Thank you, ma'am, for delivering such an insightful and engaging lecture on real-time application of graph theory. Your expertise and passion for the subject truly, and we are grateful for the valuable knowledge you have shared with us today. Your comprehensive explanation and practical examples have provided us with a deeper understanding of the topic. Your research, accomplishments, and Achievements in the field of graph theory are truly commendable, and we feel privileged to have had opportunity to learn from you. We would also like to express our gratitude to our esteemed HOD, Dr. VP Shinde sir, for their continuous support and encouragement in organizing this workshop. Their presence has been invaluable in guiding us towards academic excellence. Lastly, we would like to thank you all for the workshop coordinators, faculty members, and participants for their active involvement and enthusiastic participation. Your presence and contribution have made this workshop a resounding success. As we conclude the fourth day of this workshop, we look forward to another insightful session tomorrow. Let us carry forward the knowledge and inspiration gained today to further explore the realms of applied mathematics and computing. Thank you once again, and we eagerly anticipate to continuation of this enriching workshop.
Thank you, Ayushi. I think this session is over. Today's session is over now. Thank you so much, ma'am,
Thank you, sir. Thank you.
uh, for accepting our request in a very short interval of time. Uh, thank you so much. And I'd like to end this session now officially. Parth, yeah,
Yes,
please
sir.
end the recording.